Paulo Rangel. So another one from Brazil. Can you elaborate on how the vector equilibrium idea fits in the description of the energy gradients that creates spin?
Oh, yeah. So
Good
actually,
fundamental question.
yeah, actually, Marshall for Thrive 2, being the director of special effects. I'm sorry.
Co-directing with Foster. That's right.
Yeah.
Co-directing visual effects.
Yeah. Just did some awesome animations that he showed me the other day on that. So think of it as a vector equilibrium, not in a static form, but a vector equilibrium as a very a change in density, meaning you know the vector equilibrium has this property in which it produces angular momentum in terms of its collapsing vectors. The way what Buckminster Fuller called the jitterbug, right? So I wish I had a jitterbug here. Actually, I do. So think of this. So there's the vector equilibrium, right? Or the cube octahedron, if you like. And you can see that, like, if I rotate the top clockwise and the bottom counterclockwise, it will collapse, right? Into, you see the rotation that occurs, right? So imagine, so you have a field that has, so you can imagine, so look at the volume here and look at the volume here. And by the way, by the time it's gone from there to there, it's gone through the octahedron, the icosahedron, and now the dodecahedron, right? And so you have the tetrahedron, you have all the 5 platonic solids being produced, everything we see in nature being produced through just this motion, right? So you can imagine, like, now, as this collapse, if I had other ones that were attached to it, I don't know if I can do this. This is why the animation was so good. If you have other ones that are attached to it, that one would have grown when this one collapsed, right? So you have a change of density that's continuously occurring in a continuous information network, right? And so, and it's producing torque, right? It's producing torque in the field. So you have a density gradient. Think of the Planck field as being the densest. It's funny because we think of it as the vacuum, which when you think vacuum, you think it's really empty, but actually it's the densest field, right? And it's triangulated, so it's cube octahedrons, and then you have density change all the way to the galactic and then universal level. And at the universal level, it's 10 to the minus 30 grams per centimeter cubed. So you've got a huge change of density, right? That's occurring. So think of like huge ones of those, right? Doing the thing at the universal level, but then smaller and smaller and smaller ones doing it all the way through the fractal structure, all the way to the Planck field, right? So the torque is continuously doing this thing to it, right? The density change. Does that answer your question? Wait, you're muted.
Yes. I was trying to get a grasp a little bit more into the idea of this density, because when you think about vector equilibrium, you think, well, everything is steady, so it doesn't manifest But then maybe another question would be, who creates the gradient, you know?
Well, the gradient, this is a hard question, by the way.
Is the same guy who is blowing the balloon?
The guy that's blowing the balloon. Well, it's good. It's a good point. But I mean, like, you can go back all the way to the Big Bang this way. But what I'm saying is that, and this is something that took me a while to accept. When I discovered this, I lived in my van. It was in the mid-1990s. And I had to stop doing research for like 2 weeks or 3 weeks because I had to like integrate that concept that there's no beginning and there's no end.
It's difficult.
Of the idea, you know, because that's a human idea, you know. And so to think, oh, okay, so in that sense, then our universe is in a larger one, and that larger one is in the larger one, and so on. And each one is a change in density. Each one is, you know, less dense if you're going up, more dense if you're going down. So, and then there must be sub-Planckian units that are making up the Planck units, right? And then sub-Planckian units, and so on. So then you have, you know, so the gradient never stops. The universe is chasing its tail continuously, right? And at each scale, you can see the feedback.
Good.